This opportunity, delighted to talk about one of the areas of the research that my team is working on. Mainly, I will talk about this next generation of AI, the way or next phase of AI, I would say. So, the U.S. agency of DARPA divided the AI's evolution in three phases. The first phase is symbolic AI, and that was last century. And the first 2 decades of this century and still going on is the statistical AI. Symbolic AI was handcrafted rules, expert systems. I built my first expert system in 1988. That was chrome plating of military aircraft landing gear. Then the second phase of AI, the statistical AI, is largely driven by access to availability of very large amount of data. And so it is more of a data-driven AI. And the first decade was all about the traditional machine learning models, VECA, and all those tools that we used to use. In 2012, the major progress came in the form of deep neural networks. In 2017, yet another inflection point in the form of transformer model. And that is going on, which has led to this generative AI, which is very, very popular now. And suddenly, because of the success of this generative AI, again, AI is now, in the kind of very broadly kind of accessible, more than 100 million users in a short period for ChatGPT and so on and so forth. So all that has happened. But the third phase of AI, as DARPA is defined, is the one that is centered around hybrid AI, but one where you can explain what's happening. Now, the second phase of AI, statistical AI, while it has had some wonderful successes, it has quite a few limitations. Today, because of the success of these applications, we are not talking enough about them. But you just started to see a big shift happening this year alone. The shift happened in the context of thousands of AI leaders, researchers, technocrats writing this letter about delaying, not coming up with the next GPT for 6 months, and Hinton leaving Google so that he can, Jeffrey Hinton, so that he can talk about what he has observed recently and what he fears. And that is all along safety, largely. There are other interrelated issues, but key issue is the safety. And safety is very much tied with ethics and with the trust in AI. So this neuro-symbolic AI, which seeks to combine both the statistical and symbolic AI, it's not like taking the technology of first phase, second phase, and just putting together. There's something more to it. You have to do it differently, but nevertheless, it says that both of these aspects are very important, and that is this third phase of AI, which we kind of just starting to enter. And so I will talk a few things about it as we go along. And in the context of doing that, I will talk about some applications that are around social good or social harm area. The AI Institute currently has about 50 researchers, we just had 7 full-time faculty, 2 research faculty, and then 30 PhD students, and then other students and research staff. And already we have pretty large portfolio. In the center, you see some of the core AI work that includes large language models and generative AI increasingly. And I have not updated this slide for more than 2 years now. And on the outside is the translational AI research. The context of this is that my institute was set up from the start as university-wide institute, and it is to bring AI for the campus as a whole. So even though we are administratively situated in the College of Engineering, from the beginning we started heavy work in collaboration with. So we already collaborate with about 10 colleges and schools in the university. Ours is a tier 1 university, the state flagship university. As you can see, a lot of areas are already covered. I'll talk about a few of them as the time permits. Of the area that is of most importance to the conference today here is this interpretability, explainability, safety, trust, ethics in AI. But there are many other issues. There are many interesting things going on. There are a couple of areas that we are more or less a world leader in. This area called knowledge graph. Work in ontology and knowledge graph is something that we always led for many years. My large portfolio of work is in that area. We developed 50 plus knowledge graphs or ontologies. Many of them are public, open source. Others are used by the company I started. So both commercial and open source ontologies. And now we do many other things of various nature. We have a variety of growth areas. Neuroscience, brain science is just one of them. In fact, on my way back, I'll be visiting the brain science department at Imperial College. Okay, I can talk about all of these for a very long time, but I won't. This is a little bit about knowledge graph. This is an area that has not received as much importance as machine learning has. But it is my belief that it is going to receive a lot more importance than it has ever. Both of us, Dhawan and I, have in the past belonged to an area called semantic web, where ontologies were core component of that for the symbolic AI kind of work. But it did not scale, or the process, the way we develop those ontologies were designed by humans and was expensive and costly to develop. But now with the tools we have developed that support all of these things, we can scale this. We have one project in pharma for pharma application, and we have an application, we have ontology called Percuro, which has 6 million entities and growing with from 10 different large sources from medicine and drug development and such. And this is very important. I'll give you the simple analogy. The simple analogy is just our human brain. Human brain has been modeled for AI, developing AI. But human brain is not only about taking the data, sensory data. We get about 11 million bits per second of sensory data. But our brain is able to convert that 11 million bits into a few bits per second that we retain, that we really consciously think about and verbalize and communicate and such. So there is a massive amount of abstraction being done, right? So this has led to the Nobel Prize, Nobel Economic award called System 1 and System 2, where System 1 is the fast system, perception, and System 2 is deliberative system that thinks. So very rough analogies. System 1 is this statistical AI. System 2 is this symbolic AI. And again, I say it's very rough, and both are needed. We may observe something and we may retain it and we recall it later on. That is System 2. We observe it, immediately act upon it, so System 1, right? And our brain does this job very, very well. And we do, and we have multiple possible tiers of processing, and we can deal with different levels of abstractions. Computers today don't really. So there are two tasks, abstraction and analogy, that many of the top AI researchers have talked about as the next goal. Dennis Husband is, the the CEO of DeepMind, for example, or Andy Yang, or Etzioni, they all have talked about abstraction as a challenge for AI today. To get there, though, this neuro-symbolic AI it will be the path. We developed, for example, a tool, a platform that called Empower that develops all these. I won't talk about it today. So I'm reusing the slides for a keynote I gave at a conference that was organized by one of the UK universities, and that was on social good, AI for social good. So those applications, but they apply to many other things. Just starting with some applications where apply AI, social good. I had a national science funded project on harassment on social media. I had one on gender-based violence. Here we took 7 countries, and this was in collaboration with the United Nations Population Fund. 7 countries were Philippines, India, Nigeria, United States, and South Africa. And we studied harmful practices, sexual violence, physical violence. 17 million tweets were analyzed to get a sense of all of those things. Use of emergency relief coordination on social media. So people have requests for help, and there are institutions like FEMA in US that have resources to help. How do you connect them, right? And in one of the projects that I had called Twitteris project, this project started on the day terrorists struck India. In fact, I remember the day. It was November 6, 2008, I believe, or 2009, November 6, 2009, 6 and 7 and 8. And so I saw all this Twitter data coming and Flickr data in those days for images. And you can get each individual piece of information, but you can't get a situational awareness. You can't get a sense of what is happening. The test struck 9 places over 3 days, and that whole sense, and you can't get that. So I said, well, we need to develop a system. We can develop a system doing so. But then that system got used in Kashmir floods, where people tweeted to request rescue, saying, I'm stuck on the 3rd floor of a hotel. My child is sick. We need to be rescued. My team put together international team of coordinators. Using our tool, they identified these requests and sent to Indian Army rescue team, who went and actually picked up the things. So we continued this effort while the crisis was active. But the same system that got used during 2012 election, where I correctly predicted the outcome of the election, during 2014 Indian election for Modi, during Brexit, correctly identified Brexit results before. And at that time, I had a colleague company I founded using the technology, and one of the customers was a hedge fund, a UK hedge fund. And then we predicted 2016 election, Trump also before the election, well, on the election day before the results were out, where everybody was predicting Hillary Clinton win. We did that, and these were so many of the polls were all wrong. Many all polls were wrong, really, for Brexit and for US 2016 election. So anyway, but that technology got used for this kind of thing also. The challenge was that the number of tweets that asked for help were around 1%, and number of tweets that offered help were 0.02%. So those in our computer science know the challenge with the imbalance and that kind of problem. So there are those kind of issues that we have to solve. The toxicity, on social media is another topic. So now coming to the more of a technology part of it, and I encourage, if you want to ask a question, then I can go deep into any of the things. Otherwise, I'll remain relatively at the high level of the things. So, current language model, of course, are all about, predicting the next word, right? Or next letter rather, right? And the next word. So what is coming next? That's all, that's the key property that they have. And then, by very intelligently bringing in the chat framework, ChatGPT really took that GPT into really, very large application sphere. But what you have is what is called as distributional semantics. So with these enormous amounts of training tokens, they give you the distributive plausibilities. But they really don't understand. They're not grounded in the real world. They really don't have any understanding. So we call this natural language processing, but no understanding. They don't know that this is a real person. They don't know that this person has, we know several things about this person also, right? So they don't have, they are not grounded in physical or conceptual reality. This can be obtained by putting the semantics into the system, by putting the world model or knowledge graph into the system. I know from Wikipedia that so and so person, especially not everybody in the world, but many well-known persons. I know when they were born, and I know what are the positions they held, and you can look at what year I was elected fellow of, and all those things are there, right? So many of such things you can, or who was the 45th president of US, you can do that. To language model, you can ask the question, who was the president of US in 2048? And the answer can vary, but at once it was tried, and the answer was Barack Obama. And by using Wikipedia, we will know that that can't be, or you don't even need Wikipedia for that. By having time, you know that that can't be, because that's the future, right? And we don't know. So, but the grounding can be brought by, and real world semantics can be brought by the use of knowledge. So, no, sorry, it was not 248, but it was this one. So you could ask that, the Obama just won 2032 election. It'll give you answer. Right? What happens, and this is the just the insight that every token that a language model processes, it computes the probability with other tokens, and that some of the probabilities are very small. And in that case, there's too little actually to go by. But yet, if you are going to ask a question that deals with the tokens that are very poorly, weakly connected, it still will make up something. That is where hallucination or some of the key problems of the language models arise. So it does not have context, does not understand. So question is, what was the color of the white horse of Napoleon? And it would have a problem, right? It does not understand that you are talking about, oh, it's already given in the question. Or things like this. Mike's mom had 4 kids, 3 of them were XYZ. What is the name of the 4th kid? So, and the answer can be obvious, but it would not be able to reason that. Or here, it was asked, Amit Sheth is the director of AIC, Professor Sheth leads several research projects at the institute. And then you ask for AIC and it will make up Artificial and Integrated Intelligence System Center. Smart enough to recognize the acronym and the first letter, but it just made up, right? And my guess is why it made up this, why it made up. So what happened is that 20-30 years ago I used to work on information integration. And if you look at any corpus that where my name appears, there'll be a lot of mention of information systems, integrated systems, intelligence systems, and it made up from that, right? But there is a fact. There is a LinkedIn page with 10,600 followers that says AISC is AI Institute of South Carolina. So, and then you say, what institute does Amit Sheth belongs to? It answers, I'm not aware of specific institute, right? So now caveat. This is GPT 3.5. GPT 4 may solve some of these problems. Will it solve all problems? I doubt it, but it will solve some of the problems. These are just some of the challenges for natural language understanding, time, recency, common sense, hallucination, user explainability, application level safety. Very important issues here, right? So there has been number of AI systems that have been built which perform better than doctors or clinician or medical professional, and yet not all of them will get used or will be used. Why? Because the system gives the answer but does not explain why. Now, if you are a doctor, you are obliged to and required to follow a clinical practice guideline, a protocol that you have to follow, right? If you are asthma specialist, the discipline has set up a guideline. Asthma is divided in these 4 categories: mild, medium, severe, and severe. And that how do you categorize all of those? That is a medical knowledge. They apply that knowledge, they distinguish between knowledge, they understand transition from one level to another level. Well, this doesn't have that knowledge. So it can't explain what the result it has come up with, prediction it has come up with, or classification it has come with in that context. So then doctors can't use it. They cannot write their medical record saying, I have determined this because of that, right? So our neuro-symbolic approach takes the clinical process guideline and integrates with the language model to ensure that the language model becomes so basically a very operative term is guardrails. So we develop the guardrails and we add the guardrails to the generative AI system by using that knowledge and how to use that knowledge in the processing. Okay, so that is the core of the neuro-symbolic AI that we develop in this application example. So you have language processing versus language understanding, and you have developer interpretability. So there have been some explainability framework in AI, but they are for AI system developer. They are not for end user. They might tell you, Lime and Sharp, and those tell you that this particular technique is working on this on this data to give you this answer. That has nothing to do with what a clinician would want from the system. So that is the user explainability. You have to explain in the terms of the application or the user of the system. To be able to do that, we argue that you need the knowledge of that discipline. And so that is how we see the evolution. So this is the Instruct GPT framework on the GPT 3.5, and there are it makes things up. In spite of that, I already gave that example. Now, just as part of some insight, what happened is that for ChatGPT, they had 40 humans to capture breadth of and train the system. How can you expect 40 humans to bring in the whole knowledge about the world and diverse disciplines, in the disciplines where even the experts don't necessarily fully agree, and a lot of process is contextual in nature. You're given a blood pressure of 130/80, and it means different for a white American, and it's different. It means different for an Indian American or Asian Indian. Reason is that for the Asian Indian or South Asian Indian, South Asian person, they need the blood pressure to be on the lower side than many other ethnic groups, because they have much higher incidence of heart attack and various other genetic physical reasons for that. That has to be interpreted, right? That has to be brought in. How can 40 humans give you all that? And what they primarily use is to label. So they capture the knowledge as a label. How can reduce a complex understanding of a problem to a singular label? There's a lot of information lost when you do that. On the other hand, there do exist very large knowledge bases and knowledge graphs that that contain, I won't say all the knowledge about the world, but far more than what 40 humans can do, even for working for a long time. Right? So, example maybe UMLS or medical vocabulary. Years of evolution with many people having contributed to its development. So, human collective intelligence has been captured in very large, this knowledge bases that can be utilized. So we make the system smarter, not relying on few humans, but by tapping into this kind of knowledge base. Now, here is an interesting thing: what it takes to make system smarter and more intelligent and support understanding compared to the language models. So just pay attention to how you are understanding what I'm saying. You all have understanding of language syntax. You know what the comma here means and not. You all have linguistic knowledge, such as the one that has been captured in WordNet. You all have common sense, ConceptNet. We have broad-based general purpose knowledge. We know who is current Prime Minister of UK. And we have, we'll have knowledge of some domains, and many different people have knowledge of different domains. So humans have domain-specific knowledge. And there are ontologies or knowledge graphs for each of them. I noted some of examples here. For the top one example could be DSM-5 for mental health. Right? So just we as human get years of training. In the grade school, in early on, we are taught the syntax, we are taught the linguistics, common sense we pick up on our own, and your parents will guide you on some things, and human brain is pretty smart, learns with very few examples, and over the years we retain the facts about various things and get expert in 1 or 2 or 3 domains. That process that works in human, we try to bring into the computational system. So through the knowledge graphs or knowledge, we have explicit model of recency and common sense, supply missing knowledge, world as concepts, or that is what we do, as opposed to worlds as probability, that is what language models do, user level explanatory and safety constraints. So, there are been a variety of things over the years that we have developed. So I did an early article on shades of knowledge infused learning for enhancing deep learning, and talked about 3 broad categories: shallow, semi-deep, and deep. So the shallow infusion was essentially taking data and generating embedding and adding that to the deep neural network. So that was the shallow infusion. The semi-deep was to take the knowledge and affect the attention mechanism. And then there's a deep infusion where you have that done at multiple levels of abstraction. Different knowledge is applicable for different purpose. Common sense knowledge has certain role in understanding. Domain specific knowledge has some other role, right? And so they both need to. So this allows me to take multiple knowledge bases or knowledge graphs and incorporate knowledge in different layers of abstraction. And that is how the deep infusion system will be. And then based on that, here, just some idea of how some of the characteristics and then what you can do. So U is unsatisfactory, and M is medium, and H is high. So then I have it's just a general and this keeps on evolving, but in general you have feature abstraction layer. You have knowledge processing and understanding layer, of the system, and then you have, neural reasoning plus additional way to, do process guided reasoning. So this is where that medical practice guideline comes in. So not only it's a fact or a triple that you add to, but you also govern the process. For example, if the doctor, if you go to doctor with high blood pressure, then the doctor will need to rule out hyperthyroidism before concluding that you have hypertension. So the hyperthyroidism requires a test, and then give you. There are 7 different classes of hypertension management drugs. Calcium channel blocker or beta blocker or whatever, and that in the context of patients, health condition, the right one is chosen. Sometimes 2 of them are chosen, and then thing is given. So that there's a process, and step by step things. That is what we try to do. So before the transformers came along, we had a work where you took knowledge from DSM-5, which is the essentially material on which mental health professionals are trained. So there's there's medical literature, and these are variety of conditions: OCDs, obsessive compulsive disorder, and suicidal, this thing, and so on and so forth. So different, and these are different sources of different subreddits. These are different subreddits, and we try to apply the vocabularies used for each of these things to understand on different Reddit, and ultimately that significantly improved. So this orange part is the embedding part, and this is the neural part, traditional part, and combining them led to better set of results. So this was an example of a shallow infusion, but it still showed very good results. If you see here that on the same data set, lexical and syntactic features gave you the result with 30% error rate. All the way making improvements and adding more knowledge, it got it down to 0.025%. Massive improvement. So it still can be pretty good, although this problem is not very challenging, or not as challenging or demanding. So classification problem, you got all these results. There can be more complex computational challenge where it will not get as much improvement as this one. So after neural network, there have been various techniques that have come in. I won't discuss in detail. One of them is called K-adapter. Is an example of shallow infusion. But if you ask the native language of Manmuti is, and the answer is should be it is Malayalam. But if you think about this Roberta, the base, it gives you wrong answer. K-adapter gives you multiple answers. But good thing is that the first answer is correct, but it should not be giving all the rest, because there is no connection between one motif and all the rest of them. So the rest is made up. Right? The next one was the semi-deep infusion. And what happens here is that it allows there is an process of incorporating knowledge into the transformer layer, and it allows better clustering. Then you can see the baseline. So in a way, that is some improvement. There is another one. This is the one that we developed called KI, knowledge infused learning, TDLR, and there we are able to do better, because in the world model we can classify is related to 1418 war, Austria-Hungary, and First War and Great War in different contexts, synonymy context versus relatedness, and that kind of deeper knowledge is possible using this technique, where different entity tokens are connected to different tokens in the neural network. That gives us that. I will pass those things. So now I'll give you some example of this lifted neural representative with knowledge graph for social good. So neural network, abstract or contextualization, different types of knowledge, ability to apply process knowledge, and then improving the interaction with the system user on their own concerns. That is the broader outline. One of the corollary, one of the outcomes of these system is that it supports explainability. So what happens is that here is your text from Reddit, and we are able to map various concepts here, phrases, into the concepts in the knowledge graph. This is the knowledge graph from DSM-5. And of course, the knowledge graph also, this maps to this process, that one. And we know now that that is a subtype of disturbance in thinking. And if the definition of a term may involve disturbance in thinking, we would know that this belongs to that. So we can do this kind of taxonomic reasoning also. But nevertheless, what happens here is that here's the definition. So the doctor, clinician, is trying to determine whether this person has OCD, and then that which people have obsessive, intrusive thoughts, something else. So you try to now map this to the concepts, and that allow, and then see if that definition is satisfied. Now I can explain to the clinician why I'm calling this OCD or not OCD. Right? So there is an explainability which comes. Without that, you may still have a classification saying OCD, but you don't know why. Right? And that's the black box nature of those, neural network things. So here is a step-by-step process of, wish to be dead, non-specific active suicidal thoughts, active suicidal thoughts with some intent to act. Based on that, I come up with this label that is in Columbia Suicide Risk Scale, CSSRS. And I can tell you why I believe this is the best label, and say this is the thought process that has gone through on this data. Right? So, so this is interpretable for system users, that is clinicians and patients. That led to, for example, agreement with the expert. LLMs gave you far less agreement than the, approach that we did. Here's an interesting example of safety. So we've been working on mental health for a while, but chatbots, there is natural language generation possible, but it's hard to control what they will come with. So it's possible that the language that the chatbot uses is hurtful to the patient. As an example, here, patient is being asked by the chatbot, this is a real example, do you feel irritated or self-destructive? And doctors tell us this is not the way to do that. This will, get the patients to have negative thoughts. So converting that to, asking the more this information in a different language, using different language, is makes this system safe. So we have various processes there for inclusion of knowledge using medical questionnaire, and the safety lexicon that allows you to rule out these kind of questions and ask the more benign questions. Here is an example of explainable food recommendation. It shows you the complexity of the problem. So we have built an application where you take photograph of the meal and getting from that meal to say what is the nutrition and how it relates to your medical condition. Let's say type 1 diabetes in children. We have right now as we speak, Dr. Lisa Knight, my collaborator, is giving our system to her patients to test, how well our system works. But it requires a lot of things. Of course, you need image understanding, segmenting, and all that stuff. It requires very large data set and so on and so forth. But then you need to understand the recipe and ingredients. And you not only need to do that, you also need to come up with cooking action. The same food could be, could use baking versus broiling. The same food could be fried in a virgin or new oil or a reuse oil. The second one will have trans fat and fairly negative, bad kind of results in terms of nutrition. The first one does. The recipe is fine if you bake, but not fine if you use some other method. So that involves a lot of knowledge, cooking process knowledge, domain knowledge of cooking itself, disease specific knowledge, personalized health knowledge. And with all these, you can responses: eat this food, no; healthy ingredients, vegetables; unhealthy integrated ingredients, red meat; cooking method, baking; allergy, none; and daily value calorie within limit. Right. So that's the kind of thing that the application does. Here's a very interesting example. Just yesterday, or no, just last week, in a federal court in US essentially prohibited the government from telling the social media companies what to do with regards to disinformation. Okay. First speech trumps in any situation in US. So now government has no role in telling the social media company about disinformation. We know how poor, very negative impact, and I studied of social media on election, and it has been terrible. The 10% of the US population has agreed that they have knowingly forwarded misinformation. Okay. And a very large majority has, consumed, misinformation. So, I think the societal harm is immense of this technology. So, while I'm very aware of some huge benefits of AI, my afternoon panel statement would be that we don't, I think we are under appreciating the harmful effect of AI. It has been systemic on democracy, on institutions, and many other things. The whole politics in US is left and right is totally broken, as so is in UK. Here, this is a real tweet. I got to work with Magic Johnson last month when he came to the hospital. He donated blood. Well, the fact is that first of all, you have to recognize this is Magic Johnson or not, and then whether there is a blood donation or not. And while you do all that, you need to figure out there's a knowledge base, that tells us that Magic Johnson is HIV. He can't be donating blood. So, you need that kind of knowledge to say that, this is fake news, right? So, and we have developed a system called 5W QA based explainability that currently works on textual data. So it asks 5 questions: who claim, what claim, when claim, where claim, and why claim. And for this thing, it will create this understanding and give you the caution, or it can tell something or not tell, if you verify or not verify, and so on and so forth. Journalists, if you go to PolitiFact or you go to any of the major fact-checking websites, they can afford to check only a handful of facts, or something is fact or not, and they give the label of pants on fire to it's good kind of thing. It takes it's very time consuming job for human. So automating that using this kind of tools, or semi-automating that. For example, let the human make the final judgment, but all the things that he needs or she needs to make the judgment, give them. And for something that system cannot find, let the human do it. But it can be significant. There can be significant scaling for doing this. And then what you do is going from the processing simply to understanding, and then helping make decision. So the takeaway is that if the system were to give user level explanation, it will need to incorporate use conceptual models, vocabulary, knowledge graph, used by the user or human. Purely data-driven system can at best use explanation that ML engineers, developers can use. Knowledge is multifaceted, so I presented the diverse knowledge to support different levels of appreciation for natural language understanding. There will be different knowledge for abstraction involved in image understanding activity. The same system I showed for Magic Johnson currently works with text, but we are in the process of developing a system that works with text and images. Should you bring knowledge to the data level or embed? That's called embedding, or bring data to the knowledge level, learn from data and align with the knowledge. For less demanding intellectual activities like classification, prediction, recommendation, the former will do, which is more scalable, simpler. But for more demanding intellectual activities, decision making, taking actions with explanation, the latter will be necessary.